What I would like to do for the remainder of this lesson is a whole bunch of optimization problems. And by a whole bunch, I mean, I don't know, 4 or 5 of these things. So let's take a look at example 1. A manufacturer wants to design an open box having a square base and a surface area of 108 square inches. I paused there for a second because it's yet another box question. An open box. And you can see we have ourselves a little picture here because calculus, more or less, is the mathematics that was developed solely for the purpose of making boxes. Anyway, what dimensions will produce a box with maximum volume? I'm going to highlight this right here because that's part of the first step. What is it that we're trying to optimize? We're trying to find a box that has the biggest volume. So let's get to the first step, which is drawing pictures, labeling stuff, coming up with quantities, and hey, this part is already done for us. We want maximum volume. And part of the other thing is done for me as well, and that is the fact that we have ourselves a picture right here. It's a box that has a square base, square base, so it's an X by X. You can see here. I don't know how big the height is going to be, but I want to maximize the volume. There is one other piece of information that I do know, and that is this surface area part right here. So our surface area, which I'll call capital S, is equal to 108 square inches. I just misspelled inches. All right then, and maybe I expand out this picture just a little bit. I'm going to draw a net because I have a feeling, kind of like the other question, it's going to come in handy because we are talking about surface area here. So let's draw a net for this thing. It's a big square on the bottom, right? Because it's supposed to be an S by S. And then you have these rectangular pieces off of each one of these little sides right here. So it's sort of like the one that we made for Lee J. Monroe, except for we didn't start off with a piece of paper and cut out little edges. Okay, so I do know that this is an X by X here, and these little things are H's, all right? And we want to maximize the volume. So speaking of maximum volume, doesn't it make sense that I need a volume equation, which is called our primary equation? That's the next step in this process here, finding a primary equation for the quantity to be maximized. So primary equation, it's volume. It is a box. Volume of a box should be a length times width times height. And I can go ahead and I can substitute in some quantities already because I know my length and my width here are x and x. My height is my height, right? It's just the height there. Okay, so really my volume equation is an x times x, x squared times height. There we go. Okay, is there a problem with this equation? Why, yes, there is. The fact that we have two independent variables right here is a slight issue. So we have to get rid of one of these things, which is where this 108 square inches comes from for the surface area. Let's write an equation for the surface area and see if we can use it as a system of equations to get rid of one of these quantities right up in here. Okay, so our surface area of 108, I'm going to call this thing secondary. Secondary equation. Our surface area of 108 square inches comes from, it's just the sum of all of these pieces that are right up in here. Don't mark on your picture. It's ugly. All right, and so think back to geometry here. You just go, hey, I just add up all of the little shapes here. One right here in the middle is an x squared. We got one of those things. Plus, maybe a green up in here. Well, how big is each one of these rectangles? They're all the same. It is an x by h. xh, all of these things. And I got 4 of them. 4xh. There we go. So I now have another equation that has both x's and h's in it that we're going to solve one of these things and then plug it in here to get rid of one of those variables. Which one are we going to do? Remember, we have to keep the volume equation. It's our primary equation because we're trying to maximize volume. This is the one that we have to chop up in some kind of way. What do we want to solve this thing for? Do you want to solve this thing for x, or do you want to solve it for h? Which one is going to be easier? I think we're going to, dang it, we're going to solve this thing for h, right? Doesn't that make sense here? I hope so, because now you can't see that. Anyway, because all I have to do is subtract and divide in order to get h by itself. So that's what we're going to do next. So maybe you can do this all in one go. H is equal to, I'm going to have 108 on the other side. I'm going to subtract the x squared from it, and then I'll divide it by the coefficient of this, which is the 4x's. Ta-da! Okay, so here's our secondary equation. We're not quite done with it yet, because now we have to take this guy and then plug it in for h right here, and voila, we have no more h's. We have a primary equation that just has a v and an x in it. So I've got v is equal to x squared parentheses 108 minus x squared over 4x. And you can leave it like that, but I'm going to suggest that you go ahead and use some algebra skills. And let's clean this up a little bit. Like, for example, I can cancel out one of these guys. And let's distribute this remaining x through the parentheses. And also divide by 4. So 108. 4 goes in there evenly. I'm pretty sure that'd be 25 and 4 is 27. 25 and 2 is 27. 27x minus, I'm not sure. Well, yeah, so this is x. And then 1/4 x cubed. Yep, that looks good. So here's our volume equation. It's a cubic equation. Cubic equation, ordinarily the domain is all real numbers, which is an issue. I'm not going to use all real numbers. There is a constraint here. We base this on x. And what is x? X is the length of the base of our shape that's right here, right? So let's think about what the smallest it can be and what the biggest it can possibly be. So smallest would happen when you don't have a box. That's x is equal to 0. Now it can't actually equal 0. It's got to be bigger than that, right? Of course, so we're going to make that an inequality. And the biggest is going to be when you use your whole entire surface area for this center square that's right here. So I'm going to use my whole entire 108 square inches on just this piece because these are not going to exist. It's greedy. So this is 108 is going to be equal to x squared. And then you just take the square root of this thing. We have x is equal to the square root of 108. But it can't be square root of 108 because you don't have a box here. So our domain, written as an inequality, our feasible domain, is going to be 0 is less than x, which is less than the square root of 108. There we go. Remember how vital that step is. Now, notice again, we haven't done any calculus whatsoever. We've done some geometry, we've done some algebra, and some substitution and stuff. We got it down to the domain. The next step is to do some calculus, and we'll come back to that in the next video.